Is chapter 9, and basically it's going to put together a couple of things that we talked about in the last couple of chapters, which is our kind of grams to moles and also our equations and balancing equations. So in this chapter, we're going to talk about how we could calculate information from a balanced equation, which is very much like the lab we're kind of in the middle of that we did last week. We're waiting to dry out this week here. And we could use the equation to calculate how much product we can make. We could also use it to calculate how much reactants we started with. This is really what is referred to as stoichiometry, and we're going to talk about those type of calculations. So as we saw last time as well, there is a couple of ways that we can take a balanced equation and interpret it. Again, we could look at the coefficients and call it 2 molecules of H2 plus a molecule of O2 gives us 2 molecules of H2O. Really, stoichiometry and what we're going to be dealing with in this chapter always deals with pretty much this relationship. And that is, again, that was sometimes referred to as the mole-to-mole relationship. And as we will talk about, it is really nothing more than the coefficients from the balanced equation. So as we were doing in the previous chapter, extremely important to always make sure that your equation is balanced, especially going to mess up your calculations if it is not. So no matter what you do and pretty much anything, that should really be the first step that you do. So if you do see some coefficients in the equation, it probably is balanced, but you should still double check it. If you definitely don't see any coefficients in that equation, you should definitely take a pretty good look at it and maybe have to balance it. But that is the mole-to-mole relationship. And again, it is just a coefficient. So there are 2 moles of H2. Again, nothing written there means there's 1 mole and 2 moles of H2O. The last one is the conservation of mass. Again, we don't change any elements from reactant side to the product side of an equation. All that we break apart are electrons and bonds. So we have the conservation of the elements. So whatever their masses are on the left-hand side, in this case, the 4 hydrogens is about 4 grams. We should also have 4 grams of hydrogen really on the right-hand side. Again, they're just in different compounds. So in this chapter, we're really going to focus in on that mole-to-mole relationship that you could get from a balanced equation. So this idea and these calculations are what are referred to as stoichiometry. And really, we use stoichiometry because we're given some piece of information about a particular reaction or an equation, and we're not necessarily interested in that piece of information, but we're interested in something else in the equation. Maybe we're given how much reactants we're starting with, so we want to know how much products we're going to produce. Maybe we're given products we produced and we want to know how much reactants we started with. Or you could even do it between reactants as well. So if you know one reactant, the reactant you would have to throw in there. And the same products, you could do it between products as well. If you know how much of one product that you made, you could then figure out how much of the other product that you made as well. So stoichiometry is really a relationship, and most often we're interested a lot of times in how much product we're going to make, but we do go sort of anywhere in the equation. So when you have this arrow, and which we'll talk about, you could use stoichiometry between, again, 2 reactants on the same side of the arrow. You could do this sort of stoichiometry between 2 products on the same side of the arrow. You could do a relationship between a reactant and a product. You could also do a relationship between a product and a reactant as well. So we could use this sort of relationship to anybody in the equation. So what's the deal with stoichiometry? People get really freaked out about stoichiometry, but it really is just a conversion. And the difference is, as I might have mentioned last time at the very, very end there, instead of looking up in a table what the conversion factor is, we actually use the equation as a conversion factor between the 2 things that we're interested in. So that's really at the heart of all stoichiometry problems, is a conversion factor that you get from the balanced equation, which is, again, why it's really important that the equation has to be balanced for this to work out correctly. And rather than going to a table where it tells you like 12 inches a foot, you can have a specific sort of conversion factor between the things that are reacting or the products in an equation. Now, the units, as we will see, and we'll see as we go through some different chapters as well, we could do stoichiometry in all kinds of situations. Here we'll mainly focus on grams and moles as sort of the units that we will see. Later on this semester, we will see stoichiometry with gases. We will also see stoichiometry with liters and molarity, which is solutions. So you could do stoichiometry with solutions, with gases, with things that are grams and solids. But very common in this chapter, we're going to recall upon a couple of important conversions, which is a lot of times taking grams to moles. And once again, a reminder to do that. That is the molar mass from the periodic table that you get that from. That is the number on the bottom, tells you how many grams per mole there is. And that is the conversion factor that we use a lot in stoichiometry problems. Pretty much all beginning parts of the calculation for stoichiometry involve almost that move right there, taking something from grams to moles. And we also use on the back end of the calculation as well, a lot of times going from moles back to grams using the molar mass. So that molar mass conversion, which again, you can pull from the periodic table, about 4 significant figures is typically what we take from the periodic table. And again, you could use it as a conversion factor. You could have grams over moles or moles over grams, depending on which way that you're going. And that's very, very common in these type of problems. So the mole method is what we use here and is what we just saw in that previous sort of equation. It is really just the balance coefficient. So there's no real tricky math or anything to that other than you just have to have that equation balanced. You take the coefficients, they represent the moles of everybody that's in that equation, and you can use that again really as your conversion factor. Any questions on that so far? So there are some basic steps to, I guess I'll say basic again, basic stoichiometry problems. So we're going to talk about sort of 2 types of stoichiometry problems in this chapter. One is more of a basic, straightforward sort of stoichiometry problem. One is what is sometimes referred to as a limiting reagent problem, which is a little bit more complicated. But they all, for the most part, all stoichiometry problems pretty much have 4 basic steps. There are 5 listed here, and this could be a situation that could occur. But for the most part, steps 2 through 5 is typically what we usually will do in basic stoichiometry problems. But let's take a look at each of these steps. The first thing that you want to do is write the correct formulas of the reactants and products. So this would definitely be a situation where you are given everything in words, so you're not given the actual equation, so you got to actually write the equation. So similar to what we were doing last chapter a little bit. Remember that when you do write the equation and we go to balance the equation, you want to first start out with the correct formulas. So that's really important. Forget about the balancing part as we talked about. You want to get the right formulas and then do the balancing part. Second step here is to balance the equation. The third step is to go usually from grams to moles. So whatever unit that they give you, and it may not be in grams, it may be in some other unit, but eventually you got to get it to grams and then take the grams to moles, as we were just talking about, using the molar mass from the periodic table to do that. The reason you need to do that is really for the next step, which is actually the stoichiometry step. And that is you go to the equation and you find the 2 things you're interested in. One thing that you're interested in is typically whatever they gave you in terms of information. The other thing is what you're usually trying to find. So those are the 2 things that you're interested in the equation. You take the actual coefficients and you find the mole to mole relationship. So you go to the equation, mole to mole relationship. And that is again from the balanced equation. Once you have that, you should always be in units of moles at this point, and you may have to convert it to some other unit again on the back end of the calculation. As I mentioned, it's very, very common that molar mass here to end up with grams on the back end of the calculation. But really, you could go to any unit you want, or maybe ask some other units as well. But you may need to do a couple of conversions on the back end, but those are the basic steps. So really, we could cut this down in most cases to 4 basic steps. You want to make sure you always have a balanced equation. Nothing works right if you do not have a balanced equation. Number 2, you want to convert to moles. Number 3 is the mole to mole relationship from the equation. and number 4, if necessary, moles to some other unit. Pretty much all basic stoichiometry problems boil down to those 4 steps. And if you follow those steps in order, you'll get the right answer. You should. If something is done for you, by the way, you just go to the next step. So that's also something that people kind of screw up on. Like they go, oh, it's done for me. Let me undo it and go backwards and do it again. So for example, if it's already in moles, there's no need to convert it back to grams to convert back to moles. So don't undo anything, just kind of continue on the pathway there. Any questions on that? All right, so let's take a look at, sort of the relationships and things that we get. So let's take this one particular equation here, which is 2CO plus a little O2 makes 2CO2. So from this one equation, there are a bunch of different stoichiometric relationships that we could get. And again, it all revolves around this balanced equation, and it all revolves around the coefficients that we see in the equation. So from this equation, we could have one relationship that 2 moles of CO will give us 1 mole of O2. So that is just the coefficient. That is what is sometimes referred to as a stoichiometric equality. An equality, just like we talked about with conversions, right, are 2 things that regularly represent the same amount, right? This is a little bit different than that. Again, 2 does not equal 1. So it does not equal in terms of numbers, but as I might have talked about at the end last time, they are equal to each other in terms of the proportion that you need to kind of dump into that equation to get that reaction to basically happen. So that is why they're sort of equal to each other. We could also say for every 2 moles of CO we toss in there, we get out from the coefficient here 2 moles of CO2. And again, those relationships are nothing more than just the balanced coefficient. We could also say for every 1 mole of O2, we will get out 2 moles of CO2. So from this one equation, we have 3 different equalities that we could get. And because they are technically equalities and treated like a normal equality, we could actually have 2 conversion factors for each of these. We could again say, for example, here that 2 moles of CO over 1 mole of O2, or the other conversion factor that we could have is 1 mole of O2 over 2 moles of CO. For the second one, we could have 2 moles of CO over 2 moles of CO2, or 2 moles of CO2 over 2 moles of CO. And lastly here, we could have 1 mole of O2 over 2 moles of CO2, or 2 moles of CO2 over 1 mole of O2. So once again, from this equation, there's a lot of information that we can use to solve problems. We have these 3 equalities, and we have these 6 conversion factors. First off, any questions on how I got all those there? And again, they're nothing more than just the actual coefficients from the balanced equation. So this is what I was saying before. Basically, stoichiometry is just a conversion factor. And again, instead of looking up in a table where you're not going to find in a table like CO and O2 relationship, we go to the equation to find our conversion factors to use. We have 6 different conversion factors, 3 equalities. In a problem or a typical problem, you're just going to grab the conversion factor that you need. So you want to use all these in a problem. In most cases, you would just grab perhaps the one that you need to solve it. So if we wanted to look at something, let's just say, for example, here, let's say that we produced, in this case, 15.5 grams of CO2, and we want to know how many grams of O2 did we start with? So once again, there's those 4 basic steps for stoichiometry. So the first step is we want to have a balanced equation, which we actually do here. So the first step is actually done for us. We want a balanced equation. The second step is to take whatever piece of information they give us and convert it to moles. And in this particular case, really, when we look at this problem that I just made up, that is the only piece of information we got. And that's obviously in units of grams. So we do need to do that conversion. So here for the second step, what we need to do is convert to moles. And now, because we are in grams, the way that we can convert to moles is we need the molar mass of CO2 in this case. So we need to go to the periodic table and find the molar mass of CO2. And carbon is 12.01. There are 2 oxygens, each at 16, which gives you a molar mass of 4401 grams per mole. So this is really the second step that we want to do. We're going to take whatever piece of information they gave us and basically get them into moles. So if we did that here, that would be 15.5 grams of CO2. We're going to divide by the grams here using the molar mass from the periodic table to convert this guy into moles. And in this case, if I do that, 15.5 divided by 4401, going to give me 0.35219 moles of CO2. Here I am not rounding because I am not done with my calculations. So I don't want to round here. I'm going to take it to a few extra digits and continue on with the calculation. Any questions so far? The whole purpose really of that second step is to get whatever they gave you into the correct units so you could actually do the stoichiometry part, because the third step is always the mole to mole relationship. So the third step is we want the mole to mole relationship of what we are looking for. So the third step here is the mole to mole relationship. And that comes from the balance equation. So how do I know what I'm looking for? Well, they gave me CO2. So clearly from the equation, I am interested in CO2. The other thing that I'm interested in is what I am trying to find, which in this case is oxygen. And that would be this guy. So that relationship from the equation is 2 moles of CO2 is produced for every 1 mole of O2. That is the relationship that we could get from the balanced equation, from the coefficients. That is the big stoichiometry move right there. That gave us basically 2 conversion factors that we could use. We could use this conversion factor or that conversion factor there on the right. In this case, we want to get rid of CO2 and we want to end up with O2. Should I use the conversion factor on the left or the one on the right? Which one should I use? Yeah, the one on the left here, opposites cancel, right? So just like a normal conversion problem, that one on the left is going to allow me to go from CO2, which is really not what I'm interested in this equation or problem about, to O2, which is really what I am interested in. So that is the third step. That is the big stoichiometry step. And frankly, if you blink your eyes, you might miss it, but we will use it right here. We're going to go with 2 moles of CO2 from the equation. Gives us 1 mole of O2. That once again is the stoichiometry step. And step number 3, that's going to allow us to really convert from CO2 in this example to O2. And in this case, I'm using the whole number on my calculator, dividing it out by 2 will get us, not that, I hit some type of percent button. So let me try that again there, divided by 2. I think will give us 0.176096. Once again, I am not rounding. I'm taking it to a few digits because I am still not done with my problem. Any questions up to that point? That is the big stoichiometry move right there. So that's that conversion factor from the equation. In this case, if I was looking for moles, I would round it up, right, and put a box on it, and I would be done with the calculation. But I am not looking for moles. I'm actually looking for grams of O2. So step number 4 is we're going to go from moles to some other unit, and we do need to do that in this case. And we need to now go from moles, which you should always be in at this point. If you're not in moles at this point, you screwed up. Yeah, so you should always be in moles at this very point. And you need to go, in this case, to grams. So this is the back part of the calculation where we'll need to use the molar mass. But I need the molar mass of what at this point? Do I need to use CO2's molar mass? I need O2's molar mass. So again, we just go back to the periodic table because we have now converted to O2 and get the molar mass of that. So that is basically 2 times 16, which is our 32. So the last step we're going to do is we're going to kind of erase a couple of these conversion factors here. I'll go up here and do it. We're going to take our number that we were continuing on with here, 0.176096 moles of O2 using the molar mass from the periodic table. Here we want grams up on top, moles on the bottom, moles cancel, and that would tell me about 5.64 grams of O2. Here I am going to round at this point because I'm done with my calculation. Frankly, the only number in this problem is the 15.5, which has 3 significant figures. So we do end up with 3 significant figures. Any questions on any of those steps? Pretty much all basic stoichiometry problems are these 4 steps: balance the equation, convert to moles, mole to mole relationship, convert those moles to some other unit. Here I did it in parts and got an answer after each step, so you can see each of the steps. You do not have to do that, and frankly, they want you actually just to do it all in one calculation together without getting the answer in between. Personally, I don't care if you get the answer in between or not, but just don't round. Or you could do it obviously in all in one calculation for kind of beginning to the end there. Any questions on any of that stuff there? So this again is a basic stoichiometry problem. What that number means is if you produced 15.5 grams of CO2, you would have had to put in there, what do we get there? 5.64 grams of O2 to get that 15 grams out of that equation. So that's what that number represents. Any questions on that? Okay. All right, so that's what we just talked about. So let's take a look at a couple of examples here. All right, so why don't you try the first part up to here. Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of H2 can be formed by the complete reaction of 5.32 moles of lithium with water? So give it a go, see what you come up with. Follow those 4 steps. Once again, it is balance the equation, convert to moles, mole to mole relationship, and moles to some other unit. Okay, let's take a look and see. So once again, we want to start with the very first step, which is balance the equation. In this particular case, we're given everything in words. We don't have the equation given to us. So again, it's really important to start with the correct formulas. So lithium metal should just be Li. Remember, it has no charge by itself, reacts with water, which hopefully we know is H2O. To form here hydrogen gas, a reminder, right? Hydrogen gas is a diatomic, so it should be H2, and lithium hydroxide. And lithium is +1, hydroxide is -1, so it looks something like that is our unbalanced equation. Again, I'm not worried about the balancing part. I just want to get down the correct formulas first. Any questions on any of those there? Now we do want to do the balancing part, and I don't know, maybe like maybe a 2. I'm just putting 2s down. Let's see. We got 4, 4, 2. I think we're good. Yeah. Any questions on that? All right, so that's step number 1 checked off. Step number 2 is to take pretty much whatever they gave us and convert to moles. In this case, we are given 5.32 moles of lithium. That is obviously in moles, which means we don't need to do anything with it. So don't undo it and make it grams to grams and grams back to moles. So then we just go to the next step in this case, which is our mole to mole relationship. So once again, this is the big stoichiometry part, and we're interested in what they gave us, which is lithium. Ultimately, though, we want to know H2, which is over here. So that is the 2 things that we're interested in this particular example. From the equation, we could get the relationship, the stoichiometric equality of for every 2 moles of lithium we toss in there, we're going to get out 1 mole of H2. And again, that comes from the actual coefficients in the balanced equation. That is going to give us 2 conversion factors that we could use in this problem. We could have 2 moles of lithium over 1 mole of H2, or the other conversion factor is the opposite, 1 mole of H2 over 2 moles of lithium. Any question on how I got the relationship or the conversion factor? At this point, we're going to choose hopefully the correct one here, and we want to get rid of lithium and end up with H2. So opposites will do that. So the bottom conversion factor here is the one that we want to use. We're going to go opposite. Lithium on the bottom, which comes from the equation, and this is the stoichiometry move here. 1 mole of H2. The moles of lithium will cancel. We're basically going to take our 5.32 divided by 2. Going to give us 2.66 moles of H2, which is that. In this case, do we need to do step number 4? We do not, otherwise I probably wouldn't have boxed it there, because we're actually looking for moles, right? So in this case, we actually do not have to do step number 4, and this would actually be our answer in this case. Any questions on that? What this basically means is if we did this reaction and we put in there 5.32 moles of lithium, everything went perfect, you're not a clutch, you didn't spill anything, no side reactions happening, you should get out 2.66 moles of H2. This is what is sometimes referred to as the theoretical yield. A yield has to be a product, yeah, in order to have a yield. So it's got to be a product. This is the theoretical yield of hydrogen in moles, which obviously we could convert from moles to some other unit if we're looking for some other unit and so forth. Once again, it's the same 4 steps. Balance equation, convert to moles, already done. Mole to mole relationship, which is stoichiometry. 4 not needed in this case, yeah. Any questions on any of those steps there? All right, then do the second part of the question. So I'll just scratch out the first part. Doing the same reaction, how many grams of H2 can we form from the reaction of 81.75 grams of lithium? A couple of numbers that might be helpful. Lithium is 6.941. Hydrogen 1.008. We'll throw oxygen up for fun, maybe. I don't know if you need it. 16. All right, so see what you come up with. Let's try the second half there. Okay, let's take a look, see how you're doing. So once again, we're looking at the second half here of this question, which starts about there. And in this case, we're given 81.75 grams of lithium. And we are looking for how many grams of our H2 in this case. So once again, we want to follow the same 4 steps. We want the balanced equation, which obviously we did previously, so that's good to go. In this case, they gave us 81.75 grams of lithium. I do need to do the second step right because I need to get it into moles for the stoichiometry part to work. So that is what we're going to first do. Again, we're going to take our 81.75 grams of lithium We're going to go to the periodic table, and remember, as we saw in the previous one that I put up there, 6.941 is what you see there. So that represents 6.941 grams per mole, and we're going to use that as our conversion factor. We want the grams to cancel, so 6.941 grams per mole of lithium. Here, the grams of lithium cancel at this point, and if I stop the calculation at this point, I should be in moles of lithium, which is what I want to do. Bless you. Now, again, you could get an answer, or you can just continue on with the calculation, whichever way you want to do it. I'm okay with that. Again, just don't round if you do get an answer. So here I'm going to just kind of continue on with the calculation. But again, if you got an answer, take it to a few extra digits until the end there to round. So at this point, I am stopping at moles of lithium, which is close to what I need, but I actually am interested in H2. So once again, we're going to need to do step number 3, which is go to the equation, find the two things we're interested in. And again, it is always whatever they gave you and pretty much what you're trying to find are the two things that you're interested in. And from that equation, just like we used in the first problem there, we see that there are 2 moles of lithium, gives us 1 mole of H2. That is going to give us our 2 conversion factors, once again, that we could use in this problem. And continuing on to do the stoichiometry part from the equation, we can clearly see, as we should be setting it up here with dimensional analysis, that the moles of lithium are on top. So again, to get rid of them, we go opposite. So we do need to use the conversion factor here on the right to do that. Puts the lithium in the opposite location, moles of lithium to 1 mole of H2. That is the big stoichiometry move right there from the balanced equation. Obviously, this is from the periodic table, right? At this point, if I stop the calculation, the units I am in are moles of H2, right? Which again is, in this case, close to what I'm looking for. But in this particular case, I am not looking for moles, but I am looking for grams of H2. So I have to do step number 4 here, which is convert basically those moles into grams. Once again, we do need to remember that we're no longer at lithium, but we are at H2 at this point. So once again, I need to go to the periodic table, and every hydrogen is 1.008 grams per mole, going to give us 2.016 grams per mole for H2, which is the molar mass of H2. That again is going to be what we're using for our conversion factor. And again, we get the 1.008 from the bottom there from the periodic table. Once again, setting up dimensional analysis, we could clearly see that our moles of H2 are on top. So to get rid of them, we're going to put them on the bottom. And we're going to have a mole of H2 is 2.016 grams of H2. The moles will cancel, and that is the 4th step of the process there. So here in this case, I didn't get an answer after each step. I just did one kind of complete calculation. Remember, dimensional analysis like this, we're multiplying whatever's on top and coming back and dividing by whatever's on the bottom, basically. So we're going to take 81.75 basically times 2.016 divided by 6.941 and divided by 2, perhaps there. That's going to get us, in this case, 1187 grams of H2. First off, any questions on that calculation? Significant figure wise, this is probably the number you should be looking at, which has 4 significant figures. Pretty much everything else there is going to be kind of considered an exact number through that conversion, and you should end up with that. Once again, what this number represents is, in this particular case, if you threw in there 81.75 grams of lithium in this reaction, everything went perfect, nothing bad happened, you should get out there 11.87 grams of hydrogen. And that again is what is referred to as the theoretical yield, which is your maximum amount that you should get out of this particular reaction. Any questions on that? Yeah.
So I got 11.5 milligrams. Because I use like different grams for the hydrogen. Does that matter?
So in general, when you go to the periodic table and you pull off the molar mass from it, usually 4 significant figures is sort of what you should keep it to. And whenever you calculate the molar mass in general, 4 significant figures kind of way to go with it. So I would say in our case, as long as you gave it to 11.90, you'd be okay. Yeah. So it's just a little rounding error, but just in general, whenever you usually calculate molar mass or take it from the periodic table, kind of go with 4 significant figures. Yeah. Other questions? Because a lot of times people will just round like maybe that hydrogen just to 1 or something like that, or some books will do 1.01 or stuff like that. So, but 4 is typically what you want to go with. Other questions? Yeah. It does. So in that case, you obviously use that, it'll be okay in the end. But they started doing that lately, and when they started printing newer periodic tables, they've cut out like all the numbers on hydrogen and stuff like that. But typically in general, depending on which one you're looking at, 4 sig figs. But if obviously it only has 3, that's okay as well. Other questions? All right. So just to show you sort of what we could do with stoichiometry as well. Here we just did a calculation that told us basically that we produced 11.87 grams of hydrogen. What happens if I wanted to figure out how much of the lithium hydroxide I would have produced, right? I could actually just pick up the calculation here at the end and do the same sort of relationship to figure that out as well. So you could either start from the very beginning and do this similar type of calculation, obviously, to figure out how much of that lithium hydroxide you would produce, following the same sort of 4 steps. Or now that we know basically, how many grams of hydrogen, we can now do a relationship between these two here. So we could just do a relationship between these two. And we know that we have 11.87 grams of H2. I already will have my equation that's balanced. Second thing here would be, I'm going to convert this back into moles since I didn't have an answer or anything like that to start with. So I'm going to use the molar mass here that we just used, which was 2.016 grams per mole of H2. The grams of H2 will cancel at this point, and now I have moles of H2 back to where we're at. Now, when we look at the equation, we see that for every 1 mole of H2, we get 2 moles of lithium hydroxide. So again, we can now go and figure out our other product in this case, and we'll use that as a conversion factor. So we want to get rid of the H2. So the 1 mole of H2 will go on the bottom. The 2 moles of lithium hydroxide will go up on top. The moles of lithium hydroxide would cancel at this point. If I just want to know how many moles of lithium hydroxide, I would be done, right? But here I want to know maybe how many grams. So that was our third step, the stoichiometry step between the 2 products. And now the last thing that I want to do is figure out how many grams that would be. So I will need the molar mass of lithium hydroxide in this case, which is 6.941 for the lithium, 16 for the oxygen, and 1.008 for the hydrogen. And that's going to give me 6.941 plus 16, 1.008. Give me about 2395 grams per mole for my lithium hydroxide. Once again, we're going to use that as a conversion factor. We want to get rid of moles. So our moles of lithium hydroxide and our 23.95 grams of lithium hydroxide. The moles will cancel. Once again, we're going to multiply what we got on top and divide by the bottom. So 1187 times 2 times 2395 divided by 2.016. We would produce something like 282.0 grams of lithium hydroxide in this particular case. So again, you can use stoichiometry between products and products, reactants and reactants. You go across the arrow one way, across the arrow the other way. It all works the same way in terms of the relationship. Any questions on that there? All right. So that also, by the way, would be the theoretical yield there of our second product. And once again, you get the same answer if you started with the 81.75 and did the relationship between the lithium and the lithium hydroxide and did the same 4 steps. Any questions on that there? All right, let's try another one here. Here's the one we just did, step by step, in case you want to look at it later there. Hopefully they got the same answer. That would be good. Oh, yeah, they did. That's good. All right. All right, so why don't you try this one here? 765 grams of C6H12O6 is consumed. What is the mass of CO2 in grams? Yeah. So carbon 12.01, hydrogen 1.008, oxygen 16. All right, so once again, follow the same. Okay, so let's take a look, see how you're doing. So again, the equation may look a little scarier, the formulas may look a little bigger, but it really is just the same 4 steps. So we'll start with that. We want to balance the equation here. I do see some coefficients and it is balanced, so that's good. So we don't have to do that. Next thing we want to do is take whatever they gave us, which in this case is just this number here, and we want to convert it to moles, which we do need to do that. So once again, that's going to be our grams to moles. Molar mass from the periodic table. So we do need to figure out the molar mass here of C6H12O6. Once again, go into the periodic table to do that. 6 times 12.01 for the carbons, plus 12 times 1.008 for the hydrogens there. So that's our carbons, our hydrogens. And 6 times 16 there for our oxygens. So that's going to give us, again, going about 4 significant figures, 180.2 grams per mole, which is our molar mass for our C6H12O6. This is going to be really our conversion factor to do the second step. So we'll start with that, 765 grams C6H12O6. Once again, we're going to use the molar mass as a conversion factor. So we want grams to cancel. So that's going to go on the bottom. Moles will go up on top. And if I stop the calculation right at this point after doing the second step, we're basically in units of moles of the C6H12O6. Any questions on that there? That is really important because it gets that unit or that number into the correct unit. So we can now do the stoichiometry part of the calculation. And in this case, we want to go to our equation, find the 2 things we're interested in. So clearly we're interested in this guy, and we are interested there in the CO2, which are the 2 things that we are having this particular problem. And from that balanced equation, we can see the stoichiometric relationship of 1 mole of C6H12O6 will give us 6 moles of CO2. And again, that is nothing more than just the actual coefficient in the balance equation. So that's where those numbers come from. A reminder again, if there's no coefficient, it represents 1, not 0. So it represents 1 in this case. That's going to give us, again, our 2 sort of usable conversion factors, a mole of C6H12O6 over 6 moles of CO2, are 6 moles of CO2 over 1 mole of C6H12O6. So in this case, just continuing on here to do the stoichiometry part of the calculation, we want to go opposites. So we are going to use the conversion factor on the right here to do that. And that will give us 1 mole of what we want to get rid of on the bottom. and 6 moles of what we're looking for there up on top, which is the CO2 in this case, and our moles cancel. And once again, that comes from the balance equation, and that's the big stoichiometry part of the calculation. Any questions on that there? Hopefully, again, you can see pretty much stoichiometry is just a conversion factor. It's just getting it from a different location than a table. Now, again, if we were interested in moles of CO2, we could get the answer, clean it up, put a box around it. But in this case, we do want to go to step number 4 here, as we've done these two, because we are looking for grams and not moles. So we have one last step here, the 4th one, which is to convert these moles of CO2 into grams, and we are going to need the molar mass to do that. And once again, we want to remember at this point we have converted to CO2, so we have to go back to the periodic table and get our molar mass for our CO2, which is what we had earlier, I think 12.01 grams per mole, plus 2 times our 16 for each of the oxygens that are present. Again, that represents the carbon and the oxygen. Going to give us 4401 grams per mole, which we're going to really just use as a conversion factor as well to go from moles back to grams. In this case, we can see from our dimensional analysis setup that moles are up on top, so moles need to go on the bottom to cancel. And that's going to give us a mole of CO2 is 4401 grams of CO2. That's our 4th step there. And we got 765 times 6 times 4401 divided by 180.2. Going to give us approximately here 1121 grams of CO2. In terms of significant figures, coming back to really this number here should be about 3, which means probably should clean this up to about 1120 grams of CO2. Our 1.12 times 10 to the 3 grams. We want to do scientific notation in this case. This once again would mean that if we put in there 765 grams of our C6H12O6, we should get out theoretically about 1120 grams of CO2 would be, once again, our theoretical yield. Any questions on any of those steps? So it doesn't matter how complicated it is, doesn't matter how crazy the equation looks. It's just those 4 steps for basic stoichiometry problems, which is what we've done here. So what makes a basic stoichiometry problem? Frankly, you're just given one number, basically. Yeah, so you're given some information about a reactant, a product, whatever it may be, but you're given just one piece of information that you can convert to moles, and that makes it a basic stoichiometry problem. And you will follow these 4 steps, and it should get you to what you need. Any questions on any of those steps? Once again, here I did it all in one calculation, which is technically how they want you to learn it. But again, if you want to get an answer after each step, I'm okay with that. Just don't round to the end. All right, one last one here in basic stoichiometry problems. Try this one. How many grams is cisplatin, whose molar mass is 300.1 grams per mole, can be obtained by 0.7752 grams of K2PtCl4, molar mass 415.1. So they're nice enough to do the molar mass for you. You don't have to go to the periodic table. So that's pretty good. So see what you come up with. Okay, so since we're getting to the end, why don't you finish that one up at home, and we will start with it next time, yeah?